both of these solutions can be expressed using the relationships between just the components of the electric and magnetic fields that are transverse to the surface normal vector. So we define this concept called wave impedance. And we use the transverse components ET and HT, where ET is the amplitude and the phase of n hat cross, well, just E. That gets you the tangential component of that vector. HT is the same. In that case, when you're talking about TM incidence, that's parallel polarization, for all of the incident, reflected, and transmitted waves, HT is just H for whatever component you're talking about. But ET, the transverse component of the electric field, doesn't need a vector on top because we're just talking about amplitude, is going to be E times the cosine of the angle. So the transverse component of the incident wave is EI cosine theta I, and the transverse component of the transmitted wave is ET cosine theta t. So if we define this transverse wave impedance that would be ET over HT. And you can see how this depends on the direction of propagation. It depends on the incidence angle. And on the polarization. But for parallel polarization, you can have a transverse impedance in medium 1 that is eta 1 cosine theta I, and in medium 2, the transverse impedance becomes eta 2 cosine theta t. So then you get that the reflection coefficient for parallel polarization is eta t2 minus eta t1 divided by eta t2 plus eta t1. So when you're using transverse wave impedance like this, the expressions for the reflection coefficient look exactly like the ones from your transmission line problems. Plane waves just work like transmission lines. The transmission coefficient for parallel polarization is a little bit different because it's 1 plus gamma parallel, and what this gets you is the transverse component of the transmitted electric field. So if you want the actual amplitude of the transmitted electric field, you need to multiply by cosine theta t divided by cosine theta I. In the same way, we can use a transverse wave impedance for the perpendicular polarization. We're going to define the transverse wave impedances first. Eta T1 is going to be eta 1 over cosine theta I, because the electric field, the transverse electric field is just equal to the full electric field, but the transverse magnetic field is equal to the magnetic field times cosine theta of whatever field we're talking about. So for I, R, or T. And in medium 2, the transverse wave impedance is eta 2 over cosine theta t. Then, the reflection coefficient for perpendicular polarization is pretty much the same, eta 2, the difference of the transverse wave impedances divided by the sum of the transverse wave impedances, and the transmission coefficient here, because the electric field is completely transverse, we don't have to do that thing with the cosines. So the transmission coefficient is just 1 plus gamma perpendicular, like that. So the whole point of that wave impedance stuff is to show you that even for oblique incidence, transmission line concepts still apply to plane waves. If this makes your life easier, if this makes plane wave reflection at oblique incidence easier to understand, great. If it doesn't make it easier to understand, forget about it.